we need to solve this differential equation by Lagrange's method. So for this, first we can rewrite this equation as px into x plus y minus qy into x plus y equals to negative of x minus y into 2x plus 2y plus z. And now writing the Lagrange subsidiary equations, that is dx divided by the coefficient of p. So x into x plus y equals to dy divided by the coefficient of q, that is minus y into x plus y, equals to dz divided by what is present on the right hand side. So minus of x minus y into 2x plus 2y plus z. To get the solution, let's consider these two ratios. So we get dx divided by x into x plus y equals to dy divided by minus y into x plus y. So that I can cancel these two. So this implies dx divided by x plus dy divided by y equal to 0. And now integrating, we get log of x plus log of y equals to, the integration for 0 is a constant, and let's take that constant to be log c1. So this further implies log of xy by using the property of log, and this is log of c1. So that implies xy is equal to c1. So this is the first solution we have got. And now to get the another solution, let me use the multiplier 1, and here also 1, and here 0, and adding all these numerators. Dx plus dy plus 0 into dz, that is 0, so there is no need to write, divided by multiplying the denominator of the first ratio with 1, that is x into x plus y, multiplying the denominator of the second ratio with 1, we get minus y into x plus y, and adding. Why I have done this? So that I can get x plus y common from these two terms, right? We can equate this ratio to any of these ratios, or you can also again use the multipliers to get the new form of ratio, and this time I'm using the multiplier again to be 1, 1, and here also 1, and adding these. So I'm getting on the right hand side dx plus dy plus dz. Multiplying 1 with the denominator of the first ratio gives x into x plus y. Multiplying 1 to the denominator of the second ratio gives minus y into x plus y. Multiplying the denominator of the third ratio gives minus x minus y into 2x plus 2y plus z. Let's work on to the denominators first. From here I get x minus y into x plus y, right? And from here I get, if I take x plus y common from these two, I get again x minus y into x plus y, minus, writing this as it is, and from these two terms, if I take x minus y again common, I get x plus y minus 2x minus 2y minus z. So this gives x minus 2x, that is minus x, and from here I get minus y and then minus z. If I take minus outside, I will be getting x plus y plus z, and here negative outside, so that we can cancel x minus y from both the denominators. So finally we get dx plus dy divided by x plus y equals to dx plus dy plus dz divided by it is negative of x plus y plus z. Right? Okay, so this can be further written as d of x plus y divided by x plus y, and this can be written as, taking negative in the numerator, it is d of x plus y z, the derivative of x plus y plus z divided by x plus y plus z. And now taking this right hand side to the left hand side, we get d of x plus y divided by x plus y plus d of x plus y plus z divided by x plus y plus z equals to 0. And on integrating, we get, this is log of x plus y plus this is log of x plus y plus z equals to, I'm writing here the constant log of C2. So by using the property of log, we get log of x plus y into x plus y plus z equals to log of C2. From here we get x plus y into x plus y plus z equals to C2. So this is another solution we have got from the subsidiary equations. And now writing the general solution. How to write the general solution? It is f of C1, C2 to be equal to 0, where f is the arbitrary function. So this is f of, what is C1? It is xy, and what is C2? It is x plus y into x plus y plus z to be equal to 0. So this is the required solution. Alright, stay blessed.